Well, welcome back, everybody. Thanks for coming. Last time I gave you an exercise. I gave you this data displayed as a table or figure, whatever you want to call it, describing 100 people like yourselves, randomly selected from this class, and who are being followed for a 1 week period. And each night, at the end of the day, I call you up and ask you to develop a headache today. And what I'm looking for is the incidence of developing a first headache. So I'm assuming none of you had a headache before this class began. All of these headaches happened during the class time. Now, our president or our dean would say, gee, Fran, what are you doing with these students? That looks like a lot of headaches. And remember, this is hypothetical, although maybe it's due to Marcello's lectures, not my lectures during this. But your challenge was to describe the incidence, the development of coronary heart disease in this particular population. That was your assignment. So let me first give you one option. What if you just report that in this study of 100 people, but if all you tell me is that 15 people developed headaches, would that be enough? Well, if I didn't tell you I was following 100 people for 7 days, and all you told me is that 15 of the students developed headaches, I don't know whether that's 15 out of 15 students or 15 out of 1,000 students. So the problem is there's no point in reference if you just give me the raw number of new cases. It doesn't account for the size of this population at risk, how many students were at risk for developing a headache. It also doesn't take into account the length of time that they're being followed. If I follow 100 people for 7 days and observe 15 headaches developing, and you come along and with those same 100 people, you follow them for 2 weeks, 3 weeks, 4 weeks, you're expecting to see more cases of headaches developing. So we also have to somehow take into account not only the size of the population we're following, but the length of the follow-up period. In this case, it was 7 days. So here's option number one. Let's report a proportion. We had 100 people, 15 of them developed headaches, 85 of them did not develop headaches. When we talked about binary outcomes in the last sequence of lectures, I said one way to describe a binary outcome is to describe a pot over a whole. 15 cases out of 100 people being followed for 7 days. And that's 15%. So one way to do this, we'll call this option number one that we're talking about, is to say that 15% of your students developed headaches within these 7 days of follow-up. Now that's a proportion. Same thing we were talking about last time. But now we can give extra interpretation to this. It's a proportion of people developing an event, developing a headache. Proportions are linked to probabilities. That's what Marcello's been talking about. And now we're talking about the probability of developing a headache. Well, the probability of developing a disease is often described as a risk of developing disease. And that's why we could call this measure an estimated risk that people will develop headaches if they take this course and are followed for 7 days. We're going to call this proportion a cumulative incidence. Incidence because it refers to new cases of disease occurring during these 7 days of follow-up. Cumulative because it's not interested in when they develop the disease during the 7 days. They're just adding up the total numbers. And in total, 15 people developed headaches out of these 100 people. Now, there are some problems when reporting cumulative incidence. And the first thing is the value for the cumulative incidence depends on the length of the follow-up period. Instead of following people for 7 days, if I only follow them for 4 days, I would get a different answer for the 4-day cumulative incidence. If I go back to my original data, well, everybody from person 10 upward developed a headache in the first 4 days. Persons 11, 12, 13, 14, 15 who developed headaches on the 5th, 6th, or 7th day would not be counted as outcomes if I was interested in the risk of developing a headache within 4 days of follow-up. So in that case, it's 11. I misspoke here. 11 people developed headaches in the first 4 days of follow-up. So in that case, if I wanted to report the 4-day cumulative incidence, it would be 11 cases divided by the 100 people at risk, it'd be 11% of the cumulative incidence for that time period. If I was interested in a shorter time period, say within 1 day, or the first 4 people on that diagram developed headaches in the first day. So the cumulative incidence would be 4 cases divided by 100, or 4%. So the value for the cumulative incidence does depend on the length of follow-up. If I asked you, what's your risk of dying? And think about that. What is your risk of dying? If you think about it carefully enough, all of us have a 100% chance, 100% risk of dying sometime in the future. Hopefully it's many, many, many years from you. But if I don't specify the time, if I'm talking about a 100-year risk of dying, the cumulative incidence of dying in the next 100 years for everybody watching this class is probably going to be close to 100%. What's your risk of dying in the next 10 seconds? Hopefully no one's watching this film right now and suddenly clutches their chest and falls over and unfortunately passes on. But there is a risk of dying in the next, 10 minutes, the next 10 seconds or something like that. It's probably some very small number. So a cumulative incidence is only meaningful if you specify the time period. And that's why you have to refer to these as 7-day cumulative incidences, or 4 days cumulative incidence, or a 1-day cumulative incidence. Risk depends on the time period. Now, the other problem with cumulative incidence is the type of data we need to have to use this formula to measure cumulative incidence. Let's be more pragmatic and talk about the Framingham data, not about headaches anymore. Say we're using the Framingham data to measure the cumulative incidence of developing coronary heart disease in the next 10 years, the next 20 years, the next 24 years. That's what you have in your data set. In order to use the formula where we take the number of cases and divide by the size of the population at risk, this is what our data has to look like. Every person is going to be represented by a line. And that line either ends with the development of coronary heart disease, or that line ends with the end of the study, say 20 years into the future or 24 years into the future in the case of your data set. This is the data you'd have to have to be able to say with certainty that at the end of the study, this person did develop coronary heart disease while this other person did not, and be able to say that for everybody who was in your original population at risk. Everybody who starts off in the study. And the left-hand margins of this diagram, where the lines begin, is the beginning of the study, time 0. We want to be able to say at the end of the study whether each of these people in our population at risk either did or did not develop coronary heart disease. This is the data we need to have to calculate cumulative incidence using the formula we did in the previous example. But this is probably not what you're going to see in real life, especially if you follow people for 10 years, 20 years, 24 years, as in the case of your Framingham data. This is more likely what's going to happen. Yes, some people are going to be followed for 5, 6, 10 years, and they're going to develop coronary heart disease. Other people are going to be followed for the full follow-up period, say 20 years or 24 years, and they're still going to be free of coronary heart disease at the end of the study. Those are the easy people. In the first case, you can say, yes, that person did develop heart disease. I'm going to put them in the numerator of my calculation. The second person did not develop heart disease. He's not counted in the numerator. The numerator, again, being the number of new cases. But here's the problem. What if one of your people in your original population at risk, 10 years into the study, developed cancer and died from cancer? You plan to follow everybody for 20 years. Here's a person who died 10 years into the study. Once you're dead, you're no longer at risk for developing coronary heart disease. You don't know what would have happened to that person had they not developed cancer and had they not died. You don't know whether to put that person in the numerator or not put that person in the numerator if you're trying to use the previous formula for calculating cumulative incidence. So deaths due to other causes besides coronary heart disease are referred to as competing risks. They make a person no longer at risk for developing your outcome of interest, coronary heart disease. And those things will happen, especially if you follow for people for long periods of time, and especially if your outcome of interest is not all-cause mortality. If it's mortality of one particular type or morbidity, just developing disease, regardless whether you die from it or not, then you're going to have a problem. How do you handle these people who are lost, who are no longer at risk because they have died from another cause? On top of that, there's another even bigger problem. There are these guys, which we call lost to follow-up. In the Framingham study, you were asked to come back to a central office every 2 years to be re-examined. And when you came back for this examination, they call it a biennial examination, your risk factors would be re-recorded. You'd be seeing whether you stopped smoking or did start smoking since the last time they saw you. Elizabeth mentioned, and when she gave her STATA demo, that there were people who were smokers at the 1956 exam, the first examination in your data set, but were non-smokers at the second examination. They stopped smoking. There were other people who were not smoking at the first exam, but became smokers at the second exam. And the purpose of these follow-up examinations every 2 years was to assess people's changes in their risk factors. On top of that, the purpose of these follow-up examinations was to record all the new outcomes that happened since the last time someone saw you. Since we saw you 2 years ago, have you been diagnosed with cancer, diagnosed with heart disease, and measuring all those outcomes? Well, the intent was everyone would come back every 2 years and be re-examined. That's the intent. But people decide they don't want to participate in the study any longer. Some people might decide they want to move away from the town of Framingham, Massachusetts, and to a better climate, a warmer area. They want to move to Florida. And you don't know what happened to those people once they moved to Florida. They might have had a heart attack the day they arrived in Florida. They might have been free of heart attacks for their entire rest of their life when they're living in Florida. Point is, you don't know. So the problem in measuring cumulative incidence when you have data like this, losses to follow-up, losses due to competing risks, is it makes it very difficult to directly measure cumulative incidence. You just don't know what to do with these people who are lost to follow-up. You don't know if they developed coronary heart disease or if they didn't develop heart disease. You don't know what would have happened to people if they had not died from another cause, like cancer. Maybe they would have developed heart disease, maybe they would not have developed heart disease. The bottom line is you don't know what to put into the numerator of your calculation when you take all the cases of heart disease and divide by all the people at risk at the beginning of the study. Because there are some people you just don't know at the end of the study, 20, 24 years after the start of the study, whether they would or would not, or did not develop heart disease. That's the problem with data like these. And that's a fact of life. So what are the alternatives? Well, luckily, there are statistical methods that allow us to use data when we have losses to follow-up, when we have losses due to competing risks, to estimate what the cumulative incidence would be, to estimate what the risk would be for an individual, not using that simple formula we use for the headache data, but by using a different formula. It's based on survival analysis techniques, based on things that Marcella will be teaching later on in this class. We're going to be talking about a very special type of a survival analysis involving something called an incidence rate. But what I might have mentioned at the very beginning of this course is we epidemiologists rely heavily on statisticians and their techniques to allow us to measure outcomes. And the bottom line is going to be is that if you have these losses to follow-up or losses due to competing risks, we cannot use that simple formula we use for the headache data. We have to use something else. And that's where incidence rates are coming into play. So we'll talk about that at the next time. So I'll see you at our next session.